In this video, I want to explain the operation of the Mosfet transistor in greater detail. And to do this, I'm going to use an N-channel Mosfet as an example. Now the Mosfet has a current versus voltage curve that looks something like this. There's a flat region up here, and eventually the transistor will break down. And what I want to do in this video is relate this current in the MOSFET versus the voltage drain to source in the MOSFET. I want to relate this curve to what is going on in the channel region of the MOSFET. And by doing that, you'll get a very good understanding of how the MOSFET transistor works. So let's first start by understanding the current voltage relationship for a resistor. Let me erase this, and let's recall that from Ohm's law that resistance is equal to voltage divided by current. If I have a 0 ohm resistor and I want to plot it on this graph, I would get points along this vertical axis. So a 0 ohm resistor will plot like this. So this is resistance equals 0 ohms. So what that means is that the voltage drop is 0 regardless of the current. I can have a large current, but I have no voltage drop. So there's no voltage drop, so this is just a vertical line. Now, if I want to plot an infinite resistance, it'll plot on this axis. So an infinite resistance can have, for a very small current, or in fact it won't allow any current at all. So this current will be 0, and this voltage can be quite large. Thus I get a plot that's along this axis for the infinite resistor case. Now most resistors will be in between. So if I have a low value resistor, it will plot as a straight line, like this. If I have a little higher value resistor, the curve will move more towards this direction. Even a higher value resistor, it'll move down here. Now if I have a constant current source, let me change colors, will plot as a horizontal line. Now what that means is that resistance, if I say resistance is equal to change in voltage divided by change in current. Say for this region right here, I want to calculate this resistance on this part of the curve. Well, the current change is 0, and the voltage change can be quite large. And anything divided by 0 is equal to infinity. So a current source, this horizontal line, a current source you can think of as having infinite resistance. Now if I want to plot a voltage source, or battery, say I want to plot a battery voltage. This is 0 volts, and I have some voltage on a battery. Say it's 5 volts. So it's a constant, say this is 5 volts right here. So it's a constant voltage. So a voltage source will plot like this. So when I plot the MOSFET transistor, let me scroll down here. I plot current versus voltage. There's a resistor region. Then the resistor increases It becomes almost a current source, which is infinite resistance, then eventually it breaks down. So let's first relate this resistance region of the curve to what's going on inside the channel of the N-channel MOSFET transistor. So let's look at the structure of the MOSFET transistor on a silicon wafer. So this is the surface of the wafer. Let's say it's a p-type wafer. So this is p-type. And I have a gate electrode. I'll show here. And there's a source and drain diffusion, and I'll use a N channel, so this will be an N region. So the green here is an N-type region. N-type, this is N-type. And to make contact to the P-type substrate, there will be a P diffusion in here. In reality, there's a third dimension, so this gate electrode extends in the other direction. And this diffusion region does the same, it extends in the other dimension. So this extends, and this region extends into the third dimension, something like this. Now this region under the gate electrode is a region where the channel is going to form. And we call this length, this distance here, the channel length, or L. Now the channel width is this other dimension. So this would be the width of the transistor, W. And this P diffusion region will also extend in the third dimension. And so let's relate this width and length and what's going on in this channel region to the current versus voltage curve for the MOSFET transistor. So here is an expanded view of the channel region. I want to show what happens in this channel region when we apply a voltage to the gate. So let's say that this N diffusion region is connected to ground potential. This other N region is also connected to ground potential. And let's say that our substrate is also connected to ground potential. Now let's ask what happens when we apply a voltage to this gate. So we're going to apply a voltage that's positive at this terminal relative to this N region. And I'm going to call this voltage V gate to source, where this is the gate and this diffusion region is the source. And this can be referred to as the drain. So let's understand what happens when I apply this gate voltage. Well, we know that we're going to create an electric field beneath the gate. And we know that this P region has holes. That's predominantly, the carriers are predominantly holes. So these holes will be repelled by this electric field. They'll be pushed downwards, and electrons eventually will be attracted to this surface. And when that starts happening, there's a critical voltage that we call the threshold voltage. And I'll abbreviate that VT for V subthreshold. And when we reach V threshold, perhaps it takes 0.6 volts or 0.7 volts, we get a strong enough electric field to invert this P-type wafer at the surface into an N-type. And when that happens, we have like a bar of silicon. Let me change colors for that bar. Let me make that a green so we know that this bar of silicon is an N-type region. Now, so we form a diode, a junction diode, from this P region to this N region. And the same thing happens in this channel. We form a junction diode, this P, to the N region in the channel. We also have a junction diode here. And so there's a depletion region that extends into this P-type wafer. So I'll draw that here. So as we increase the gate voltage, we make this electric field stronger. And what we do is we shove this N region down further. And of course our depletion region extends down further. So as we apply more gate voltage, this channel region becomes thicker. It becomes lower resistance because we have a greater path for current to flow laterally in this region. Now, as we apply a very strong gate voltage, we drive this channel region down even further, and the resistance of this channel region becomes less, and this depletion region will be driven down further. So if we plot what's happening here in terms of current and voltage, as we form the channel, initially it's rather high resistance region. So as a slope like this. Now recall that this region would be infinite resistance. And as we increase the gate voltage, we drive the channel down further and the resistance becomes less. And as we increase the gate voltage even further, we drive the channel down and the resistance becomes even less. So in this direction, the resistance is decreasing and our voltage from the gate to source is increasing. So let me label my axes here. This is current in the channel for a very small voltage across the channel that we'll call V drain to source. Recall in a previous video that we said that resistance was equal to the resistance of a thin sheet. We called it the sheet resistance times the number of squares, which was the length divided by the width. So if we have a sheet of material and we have current flowing into that sheet in this direction, which is the direction of the length, and this we define as the width of the sheet, W, and length divided by width becomes the number of squares. For example, here we have about 2 squares. Now this MOSFET transistor, there's a formula for this sheet resistance, R sub S. And R sub S is approximately equal to 1 divided by some constant. So there's a mu, which is channel mobility, times epsilon, which is the permittivity, divided by a thickness term. And we'll discuss these terms in a second. This is times the width. Whoops, let me undo that. That's not quite correct. That gets multiplied times the voltage gate to source minus the threshold voltage, V sub T. Now notice that as the V gate source term increases, that the denominator becomes larger and the sheet resistance becomes smaller. So let's relate what this equation is saying to the behavior of the transistor. If we have the surface of the wafer, we have a source, a drain region, and a gate electrode. And we apply, say this is source, we apply a V gate to source. That's bigger than the threshold voltage. And we invert this channel region. Let me change colors. So as we apply a stronger electric field and a higher gate to source voltage, we drive this channel region down. And that causes the sheet resistance to become lower because there's a greater path here for the current to flow as this channel is driven down. So let me explain what this mu term is. This mu term is a channel mobility in this region. This epsilon term, or this epsilon, is a permittivity of the glass region, or the region under the gate electrode. And this TOX, is the thickness of this region under the gate electrode. So TOX is this dimension. So what I really want to illustrate here is that as you apply a gate voltage relative to a source and drain that are at ground and a substrate that is at ground, you create like a sheet of silicon under this gate electrode. And as the gate voltage increases, the thickness of the sheet increases, making the resistance lower. Now let's explain what happens when our drain and source voltage are not equal. Let's presume that this is a source and this is a drain. Now the drain and the source are interchangeable in terms of the way the fabrication is done. What distinguishes the source from the drain is the voltage level. And for an N-channel or an NMOS transistor, the source is usually at a low voltage, and it can be at a low voltage such as ground. And the substrate, let's say that that is also at ground. Let's examine what happens when we can change the drain voltage to a higher voltage than ground. So we're going to put a battery in here. Let's say this terminal of the battery connects to ground. And this is an adjustable battery, so I'm going to put an arrow through it, saying that we can change the voltage of this battery from 0 to 1 volt to 2 volts, whatever we wish. And let's say that we also have a battery from the source to the gate. So this is the voltage gate to source. And again, we can make this a variable. So if we start the drain at ground, we'll say this voltage source is 0. So our substrate is at ground, the source is at ground, and we start increasing the gate to source voltage. And when we increase that enough, we overcome the threshold and we start forming an N-type region at the surface. And as we increase the voltage gate to source even more, we drive this channel down deeper and we form a resistor in this region. Now let's ask ourselves, what happens as we increase the drain voltage? Right now we have it set at 0 volts. But what if we set that a little higher, perhaps at a volt? Let me erase some of this. And let's look at what's going to happen. At this part, I have a strong electric field because this source is at ground. So my channel goes down very deep. Now, as I raise my drain voltage, the electric field here becomes weaker. And so the channel is not driven down as far. So if I plot my channel, at the source I have a deep channel, then at the drain, the channel is not as deep anymore. So on my current versus voltage curve, my resistance is increasing. So as the channel was driven down very far, it had lower resistance, but as this region is thinning down here, the resistance is increasing, and I'm diverging from this curve. I'm going a little higher resistance, so this slope changes. Now, if I increase my drain voltage even more, let me erase some of this channel region. So let's increase the drain voltage even more. And again here, let me change my pen. The channel is driven very deep here, but at some point I'm going to increase the drain voltage enough that I'm going to essentially have only a VT drop. So this is going to be higher voltage relative to the drain by the threshold. So I'll just be starting to form the channel at the drain terminal, but at the source the channel is quite deep. Now, under this condition, I'm reaching a point where this device starts to behave as a constant current source as I raise my drain voltage further. This channel is pinched off. So if I increase my drain voltage further, this channel will even pinch off more. So let's erase this channel here. And let me change my color. So the channel can even move further this way. So my effective channel length has decreased. This will be my L effective. In this region here, let me draw the depletion region. So we have a depletion region. As this drain voltage increases, the depletion region becomes larger under the drain. And there's a very strong electric field that points in this direction, in this depletion region. What happens is these electrons are attracted to this drain region. So they just shoot across this depletion region in such a way that we have more or less a constant current source. And there is an equation that we can use to describe this part, this constant current region. Let me change colors here. And this equation is for the drain current. So the current flowing in the drain is equal to approximately the mobility times the epsilon divided by the oxide thickness. Same terms we discussed before. There's a factor of 2 in here. This is times the width of the transistor divided by the length effective, EFF, the channel length, which is this term. And that gets multiplied by the V gate to source minus the V threshold. And this term is raised to the second power. It gets squared. So we can see as the voltage gate to source increases, we go from a curve like this. As we increase the voltage gate to source, the resistance is smaller and the current becomes larger. So this term, or this equation, applies to this region where things are looking like a current source. And notice that as we increase the drain voltage, this L effective, this term here, gets a little smaller because this channel region moves over further to the left, and that decreases this effective channel length. And decreasing the effective channel length will tend to increase the slope a little bit. It'll give us a little more drain current. So let me plot this as I drain versus V drain to source. So this small increase in slope is channel length modulation, or L effective, getting a little smaller. And since L effective is in the denominator, it makes the I sub D just a little larger. So let's summarize what's happening here. Let's redraw this current versus voltage, where this is the voltage drain to source. This is the current in the drain. And as we apply a gate voltage to this NMOS transistor, if the drain to source voltage is 0 or very small, we have what looks like a resistor. But as we increase the drain to source voltage, we decrease the channel region near the drain, and this slope decreases until we reach the pinch off, and this curve becomes relatively flat and eventually breaks down. Now, if we increase our gate to source voltage more and replot this curve, for a higher V gate to source voltage, we have a lower resistance, and then the channel starts to fall off near the drain. We end up with a constant current, and eventually it breaks down. So as we increase the gate to source voltage, we move this way, and our curve moves this way. So hopefully this gives you an overview of the NMOS or N-channel transistor and how the channel region relates to this curve. And in this part of the curve, you can think of the channel as just being a bar of silicon, where the gate electrode is up here and the source and the drain regions are here. So now in this part of the curve, the channel is more like this. It gets pinched off. And over here, the channel is deep over here and will even pinch off sooner.